Hi, Margaret. I don't know how far you've gotten yet, but I wrote a little video here for acids and bases. We're not going to do any numbers, but just definitions. So probably the thing that the chem books emphasize the most is the definition of a Bronsted-Lowry acid or base. It's a very broad definition that includes a lot of types of molecules. If you want me to talk about other definitions, I can, but this is the one that's most common. So Bronsted-Lowry definition of acids and bases says that an acid is a proton donor and a base is a proton acceptor. There are many different kinds of molecules that fall in these categories. Later on, you might see a generic expression like HA representing an acid, but I think sometimes students get confused by that. And here's what I mean. Here's an example of a Bronsted-Lowry acid that's a molecular compound. It's a neutral compound that has an H that can be given up, in this case, to water. So if you look carefully, the red circled H that was on HNO3 gets plucked off. So that means that this molecule is acting as a Bronsted-Lowry acid. Now, the water is acting as a Bronsted-Lowry base because it's accepting a proton, and it turns into the hydronium ion. So I've circled the red circle around an H that was on this acid and gets taken by a base to become this hydronium. And look what's left over, the nitrate ion. But don't make the mistake of thinking that only neutral molecules can act as acids. Here's an example of a cation that acts as a Bronsted-Lowry acid. So NH4 plus has an H that is given up to water to give ammonia, which is neutral, and a hydronium. So in both cases, the first species that I've drawn is the Bronsted-Lowry acid. Not only can cations act as Bronsted-Lowry acids, so can anions. Here's one here, HSO4 minus. You can see the H that I've circled, gives it up to water, and then you have a sulfate ion and a hydronium ion. So in each of these three cases, a hydronium ion is one of the products because water took away an H. The fourth category I have is a hydrated metal cation. So this looks really kind of complicated. It's an iron atom in the middle of 6 waters with a total of a 3+ charge. But notice what I've circled there. I've circled one of the H's, which is given up to water. I didn't draw the water because I ran out of space, but it loses to make a hydronium ion again. So what we've seen between these two pages are 4 different examples of Bronsted-Lowry acids. There are many kinds of Bronsted-Lowry bases. Those are things that accept protons. So here, ammonia, NH3, is acting as a Bronsted-Lowry base because it's accepting a proton from water. This anion is acting as a Bronsted-Lowry base because it's accepting a proton from water, and you can see what's left over. In both of these cases, you leave a hydroxide anion, and then you've got the new species, which added an H. So, acids which only have the possibility of giving up one proton, one H+, are called monoprotic. Polyprotic acids are capable of donating 2 or more protons. So here's an example. Phosphoric acid can lose actually 3 protons. Each of these, we'll learn, has its own equilibrium constant. So I can call that capital K1, K2, and K3. They are different values. Usually the first one is larger than the second one, which is larger than the third. We're not going to worry about those right now. But notice what's happening each time. The very first molecule, the molecular form, loses a proton, then loses a second, then loses a third. And you can see in each of these you're creating a new H3O+, and then the product. Not only can polyprotic acids exist, you could have polyprotic bases. So here's one right here, carbonate. Carbonate is going to take a proton from water, and then that product, hydrogen carbonate, can take a proton from a different water to actually add 2. These equilibrium constants are going to be different, and as I said before, the K1 is going to be larger than the K2. Finally, I'm not sure what word your textbook uses. My textbook uses the word amphiprotic, but I've also read books that say amphoteric. Those are species that can act as an acid or a base. You have to look carefully at the reaction. Here's H2PO4 minus acting as an acid. It's giving up a proton to water to make a hydronium ion and hydrogen phosphate 2 minus. This same molecule, H2PO4, is taking a proton to make H3PO4 and a hydroxide ion. So that's called amphiprotic or amphoteric. Finally, this theory of describing these kinds of reactions introduces a concept called the conjugate acid-base pair. What I've done here is I've taken one that you showed you earlier, the hydrogen carbonate ion, acting as a base. So it gives up, it does not give up. A base takes and accepts a proton from water. So water is acting as an acid, and the base accepted a proton to become H2CO3, which of course is an acid because it has the potential to lose a proton if the reaction were to reverse. So each of these, each red arrow shows a conjugate acid-base pair. All right, I have to get ready for class, but I'll talk to you a little bit later. Bye.